Hello everyone, I am Roberto Vargas and welcome to our presentation and our final project. We'll be showing a live demo of an application which is of an encryption app, and it will also show encryption and decryption of messages using two popular encryption algorithms known as AES and RSA. So first we will have the introduction. So this is what we will cover in our presentation. We will first walk through the project goals, then we will explain the background and core components of implementation, and finally we will have a live demo and show the integration of the project. In today's digital world, the need for secure communication is more crucial than ever. So we build a standalone desktop solution, which is a lightweight application for local secure messaging that uses proven encryption algorithms. Moving over to our contributions. So we are providing a clean graphical user interface, or GUI for short, using C++. We are also implementing an AES encryption for fast, secure, symmetric encryption. And we also are integrating the RSA encryption for secure key exchange, which is also asymmetric compared to AES, which is symmetric. And we are also enabling features like message history, key generation, copy and paste, and a selectable encryption modes. Moving over to the background information. So before diving into the code, we will discuss some of the cryptographic algorithms used in the project. So first off, we have the AES, or Advanced Encryption Standard, which is a fast symmetric block cipher, encrypts data in fixed size blocks of 128 bits. AES also operates through multiple rounds, where each round includes the subbytes, which is a byte substitution, shift rows, which is when it is shifting rows of the bytes in the matrix or matrices, mix columns, which mixes data across the columns, and finally the add round key, where is the exception or with part of the key. And it is a slower but secure. Oh, sorry. And then where RSA, oops. And then RSA, which is a slower but secure asymmetric algorithm, meaning it uses two different keys, a public key to encrypt and a private key to decrypt, which is perfect for the secure key exchange. And then moving over, Killian will take over on the implementation. Thank you.
Hi everyone, my name is Killian, and I'm going to be expanding upon what Roberto spoke about regarding the application that we did, and I'll be going further into detail about the implementation of the project, and I'll be talking about the two algorithms that we used, which is AES and RSA. AES is good because it's fast, it's block-based, and it's great for handling large amounts of data. RSA is good because it's safer. It's great for key exchanges in that sense. So we use both of those algorithms in a hybrid setting. I'll talk about that a little bit later. Um, but just a quick refresher on AES. It's 128 bits long, so it gives us a lot of possibilities when it comes to keys. And it's chopped down into blocks, and each block is 16 bytes. So think about it like a paper shredder, and each one of those pieces is 16 bytes long, and those get scrambled up. To start off with AES, we generate a random 128-bit key using a random number generator, and we pad the message, and the length is a multiple of 16 bytes. And so what we do is we encrypt each one of those 16-byte blocks independently. We use the electronic codebook mode, which is easy to code. If we were to try to implement something for production or something that we'd like to actually implement for, let's say, the general population, well, we might switch to maybe a safer mode like CBC, for example. So, the result is that the ciphertext is the same length as the padded message. It's not possible to read without having the exact key. And again, as I stated in the beginning, AES needs the secret key ahead of time. So again, AES by itself is not enough. We do need to have RSA as well. If two people are very far apart, how would they share the key without letting attackers copy it? And so we also implement RSA, which is an encryption system that's with a separate public and private parts. So I'll be talking a little bit about that as well. And so to start off with the RSA implementation, we generate two large primes, which we call P and Q, and we use the Miller-Rabin primality test for that. And then we compute n using P and Q and phi as well. Phi helps with the math in this case. And then we also choose E, which has to be between 1 and phi. So it has to be greater than 1, but less than phi in this case. And then what we do is we use the extended Euclidean algorithm to find D. And so then what we get is, we get the public key, which would be N and E, and then we have the private key, which is N and D. And of course, the public key is something that could be shared. It can be in the internet. And then the private key is what has to be kept secret. That's how we keep the message safe that we want to send to a third party. And then you have the encryption formula, which is cipher equals plain text mod n. And then to decrypt, you have the plain text equals cipher mod n. And in this scenario, there's a way to encrypt, and then later on be able to decrypt the message that you do. And so also the way that we use both of these implementations is, we generate the AES key, and then we encrypt that key using a recipient public key from the RSA, and then we encrypt the actual message with AES, and then there's two things that we send. We send the RSA encrypted AES key and the AES encrypted message. And again, the reason that we do this is because, for one, the AES is fast and it handles data fairly quickly. And we use RSA again for security. It makes sure that the intended person is the one getting the message. So on the recipient side, we use the RSA private key to unlock the AES key, and we use the unlocked AES key to decrypt the message bytes, and then we remove the padding, and then it shows the original text. And this takes a relatively small amount of time. Let's say if you're using a regular laptop, it has to be fairly quickly, and this is a fairly quick implementation that we use. So it's pretty much almost instantaneous, as we're already used to doing. So, so that's why we thought that using a combination of both would be the best way to make sure that it's secure and that it's also efficient. So next up, we have Ruchir, and he's going to show you guys how this is going to look in a GUI situation. And so stay tuned for that. Thank you.
Hi, I'm Ruchir K.C. Reddy. I'm a student from Practical Aspect of Cryptography, and I'm going to show you the implementation of our project. First, to describe about the project, it is an advanced hybrid cryptography application that combines the RSA and AES algorithms to provide the robust security for message management. We have used these two algorithms to manage two large prime numbers that which are selected and multiplied to create a modulus, and then public and private keys are generated from this modulus, and the public key encrypts the data that only a private key can decrypt. And why when it comes to why we use the RSA algorithm, it is a good algorithm for secure key exchange without requiring a pre-shared secret key, and we also used AES algorithm that uses a single key for both encryption and decryption, also processes the data in fixed size blocks of 128 bits. It applies multiple rounds for substitution and permutation. We used several dependencies such as C++ compiler, FLTK, also known as FastLight Toolkit, OpenSSL, GMP, CMake, and these are used because C++ gives us the critical features for modern C++ development, including improved memory management, lambda expressions, and standard library enhancements. Coming to the FLTK, lightweight, it's lightweight and cross-platform GUI toolkit for minimal dependencies. Since we are using C++, which is a very older programming language for our project, it's suitable for us to use this toolkit to provide a GUI graphical user interface of to demonstrate our project. And moving forward on how it is implemented, the AES 256 key is generated for each message, and RSA public key is used to encrypt this AES key, and plain text is encrypted using the AES key, and the encrypted message and RSA encrypted AES key are stored together, and encrypted messages are stored with the encrypted AES keys, where no plain text or keys are even stored unencrypted. Coming to the decryption process, the RSA private key decrypts the stored AES key, and this recovered AES key is kept in a memory only temporarily. And the recovered AES key is used to decrypt the message, and once the decryption is complete, the AES key is securely wiped out from the memory. Coming to the security considerations, as I just mentioned, the keys are securely wiped from the memory after usage, and um, uh, constant time operations are used whenever and wherever possible, and cryptographic failures are handled without revealing sensitive information. Coming to the technical specifications of our project, uh, 2048 bits is used for the RSA key size, which is strong, which gives us the strong security with reasonable performance, considering the project. And the AES 256 CBC with the random initialization vectors gives us the AES configurations. And the key derivations are produced with the strong random number generator for AES keys. Moving forward with the demonstration, we are using the Replit online tool to use all these dependencies together, which is easy to import just by mentioning it in the code to use these dependencies. And now I'm going to show you the source code. This is the AES. This is the code where the AES keys are generated, where the encryption and decryption happens. And this is the header file for the AES, where everything is mentioned to call out all the CPP files. This is the main C++ file, and this is the RSA C++ file where the cipher block is used to generate the keys and encrypt and decrypt the messages. Now I am going to run the code for all of us to show, and there we go. So coming to the UI, since we are using the C++ and GMP for the UI GUI, it looks a pretty old one like the Windows XP, but pretty sure it works. And here we have three text fields, where for two of which we can edit, and the third one shows us the message history. In the first one, we can enter the text to first generate the keys. Let's just say testing the project, and then click on generate keys. The algorithm is used to generate the keys. Since this key is highlighted, this a key is going to be used for encryption and decryption. Let's say for this is the practical demonstration project. So let's just say this is the message that we want to encrypt. We just need to click on encrypt, and we can see the encrypted message, and also the key that is used for the encryption. Of course, this is used. This shows the key name, not the actual key that is encrypted, that is used. This is just the key name which we are giving as the user input while creating the keys, while generating the keys. With this, you can just copy the output, and you can just paste the output over here to decrypt it. It usually it's basically, instead of copying it manually, we had a functionality to copy the whole output and paste it in the first text box to decrypt the message, to decrypt the encrypted message. And once we click on decrypt, it decrypts and shows the original message, which is, in this case, this is a practical demonstration of the project. And the third text box shows us the message history. This was done on 23rd April at 1:39 a.m. I'm not sure why this is the timings that is being showed, but as of now, I'm in the EST. It's 9:41 somewhere around. So when we check on these details, when we click on these details, we can see the key name that is used, the original text, and also the encrypted text. And we can even go back from the message history, and if you want to delete this message, we can delete it from here as well. Yeah, and these we had several functionalities here. First, to generate the keys, use multiple keys, and we use the same text box to type in the message by clearing the key name, and we click on encrypt or decrypt to demonstrate the cryptographic system. And yeah, this is the project we have been working on for this semester. Thank you.